The universe is playing a grand game of hide-and-seek. It's a cosmic mystery woven into the fabric of space and time, a silent, invisible force that sculpts everything we see, yet remains completely hidden from our view. Before we dive deeper, subscribe now if you enjoy this kind of thinking. We call this enigma dark matter. It's not dark like a shadow, but rather because it doesn't interact with light at all. It doesn't emit, reflect, or absorb any form of electromagnetic radiation, meaning every telescope we've ever built is utterly blind to it. Think about everything you know of the cosmos, the stars, planets, and vast clouds of gas. All of that makes up a shockingly small fraction of what's out there, roughly 5%. The rest is a cosmic ghost. About 27% is dark matter, and the other 68% is the even more baffling dark energy. So if we can't see it, how do we know it's there? We infer its presence from its gravitational pull. The first major clue came from the way galaxies spin. When astronomers measured the speeds of stars, they found something deeply unsettling. According to our understanding of gravity, stars farther from the center should move much more slowly. But that's not what we see. Instead, the outer stars are moving just as fast as the inner ones. The only way to explain this is if the galaxy is embedded in a massive, invisible halo of extra matter, providing the gravitational glue needed to hold it all together. Without it, these galaxies would have spun themselves apart billions of years ago. The evidence doesn't stop there. Einstein's theory of general relativity tells us that mass warps spacetime, so a huge amount of mass, like a galaxy cluster, can act like a cosmic magnifying glass, bending the light from more distant galaxies as it passes by. This effect, called gravitational lensing, allows us to literally see the impact of the invisible. By mapping these distortions, scientists can calculate the total mass of the cluster and consistently find that there's far more mass than we can account for from its visible stars and gas. The map of gravity's fingerprint reveals a colossal structure of dark matter. On the largest scales, dark matter acts as the universe's grand architect. Computer simulations show that without it, the gravitational pull of ordinary matter alone wouldn't have been strong enough to form the vast, web-like structures of galaxy clusters we observe today. Dark matter provided the scaffolding, creating dense filaments where ordinary matter could then collect and ignite into the galaxies we know and love. So, what is this stuff? The truth is, we don't know, but we have compelling candidates. The leading theory was a class of particles called WIMPs, or weakly interacting massive particles. These hypothetical particles would be heavy, slow-moving, and would only interact with normal matter through gravity and the weak nuclear force, making them incredibly difficult to detect. Another popular candidate is the axion, a much lighter ghost-like particle. There are also ideas like sterile neutrinos, or even primordial black holes formed in the first moments after the Big Bang. The list of candidates is weird, wonderful, and still growing. This uncertainty has launched one of the most ambitious searches in the history of science. To catch a ghost, you have to build some very clever traps. One approach is to go deep underground to shield experiments from cosmic rays. In labs buried a mile beneath the Earth, scientists have built enormous vats of ultra-pure liquid xenon. The hope is that a dark matter particle will drift through the Earth and bump into an atomic nucleus in the detector, creating a tiny flash of light that sensitive instruments can pick up. Another strategy is to look for it in space. Experiments like the Alpha Magnetic Spectrometer on the International Space Station aren't looking for dark matter directly, but for its death rattle. If two dark matter particles were to collide and annihilate, they could produce a shower of familiar particles, like gamma rays, that we can detect. Finding an excess of these signals coming from the center of our galaxy would be a smoking gun, and finally, we can try to make it ourselves. At particle colliders like the Large Hadron Collider, physicists smash protons together at nearly the speed of light. The goal is to see if any dark matter particles are produced in the collision. We wouldn't see the particle itself, but we'd detect its absence. Energy and momentum would appear to go missing, carried away by an invisible particle that escapes the detector. So far, all of these searches have come up empty, but each null result is not a failure. It's a crucial clue. It tells us what dark matter isn't, allowing us to rule out certain theories and refine our search, pushing us to look in new places and think of even more creative ideas. Dark matter is a fundamental part of our cosmic story. Solving this puzzle won't just add a new particle to our textbooks. It will revolutionize our understanding of gravity, particle physics, and the evolution of the universe itself. It will tell us why galaxies look the way they do, and it could hold the key to the ultimate fate of the cosmos. The hunt is a testament to human curiosity, our relentless drive to understand the universe even when it presents us with a profound and stubborn mystery. The answer is out there, hiding in plain sight, and with every new experiment, we get one step closer to finally turning on the lights.
If this made you think, there's more waiting for you. Subscribe and drift into deeper thoughts.